This is a clip from the movie Interstellar. This sequence is a masterclass in illustrating science, with actual physics being used to create this stunning black hole. This representation is the closest we've gotten to accurately depicting what these cosmic giants look like in all their glory. It's truly amazing. But we can't start there. Let's go back. The study of black holes only really got started in 1915 with the creation and publishing of Einstein's general relativity theories. We can go back even further, to the late 500s BCs with the Greek philosopher Anaximander. Anaximander is regarded as one of the first cosmologists, and his initial model of the universe is quite interesting. He believed that the Earth was in a series of spheres, each with holes of varying sizes that let light come through from the fiery outer layers, thus explaining the stars and sun. This is one of the more notable examples, but certainly not a unique case. Another example would be the myth of the Peconic Kisik. This myth is from the indigenous Cree people of present-day Canada, and talks about what we now know as the Pleiades cluster. That's this collection of 5 stars here. The myth talks of the Star Woman, the first person on Earth. She falls down from the primordial sky island to a hole in space, the gap in the middle of the Pleiades. She then lands and proceeds to work on creating humanity with the assistance of the local wildlife. But for our purposes, the point of this myth is the idea of a hole in the sky being repeated once again. Now let's jump ahead to the fun stuff, to the real beginning of the study of black holes, to Berlin in the year 1915. Here, Einstein has just published his theory of general relativity, and the games have begun. These equations allowed German physicist Karl Schwarzschild to write an equation that would prove to be monumentally important to the study of black holes, the equation for the radius of a black hole, otherwise known as the Schwarzschild radius. This would be the match that lit the fire of black holes. See, black holes had been hypothesized as early as 1783 by an English rector, John Michell, and again in 1798 by a French mathematician, Pierre-Simon Laplace. But until 1915, they had been theorized about but never proven. In fact, they were usually the subject of irritation and outright denial by notable scientists at the time. This was primarily because, frankly, black holes are hard to think about and make no sense. The scientists of the time thought that there was simply no way the stars would behave like this in the real world. But after Schwarzschild's equations and the new perspective brought on by general relativity, scientists were forced to consider the possibility that these impossible cosmic flukes were in fact not flukes at all, but a natural phenomenon that's out there right now. Being forced to confront the existence of black holes didn't make scientists such as Arthur Eddington change their tune at all. Even Einstein himself wrote a paper wherein he said that black holes do not exist in physical reality. For the next 5 decades, research into black holes was mainly trying to prove that they couldn't exist. This led to a tug-of-war, with research seemingly proving that they could not exist out in the real world, only to be proven wrong with new research, only for that research to then be proven wrong. This back and forth eventually brought in scientific heavyweights like Sir Roger Penrose and even Oppenheimer himself into the fray, before it became Cillian Murphy. It was also not without its casualties. A young physicist named Subramanian Chandrasekhar scored a point for the existence of black holes when he showed that electron degeneracy, a phenomenon that was currently the linchpin disproving black holes, actually didn't disprove black holes at all. After he proved this, Arthur Eddington, still firmly against the idea of the dark stars, as they were referred to at the time, shot down Chandrasekhar's research and scorned him in the eyes of the wider astronomical community. This hurt him deeply, but his story does have a happy ending. In 1983, his work was eventually proven correct, and he won the Nobel Prize for his efforts. Eventually, after the scientists came back from World War II, a new team took up the mantle of the study. Their efforts were spearheaded by this guy, John Archibald Wheeler. Once this new group of scientists started leading the research, the battle to prove black holes started to come to a close. Wheeler was actually the one that started it. He began against the idea of black holes, but eventually came around. He actually ended up being the one to coin the term black hole when he wrote a paper in 1962, Causality and Multiply Connected Spacetime, which elegantly proved a number of things about black holes. The last nail in the coffin for the black hole deniers was when Roger Penrose published a paper titled Gravitational Collapse and Spacetime Singularities, a veritable masterclass in theoretical physics that cleared up any doubts about the dark stars that may have been left after Wheeler's paper. After this point, black holes finally had a firm base to stand on, and by the 1970s they had been generally accepted by the scientific community as real. Up until now, this has mostly been the tale of the astrophysical phenomena that is black holes. It's been their history. Now we can dive into the meat of this story. Throughout this recollection, you may have noticed an interesting thing black holes have been doing. They've been linking things. General relativity to standard physics and theories, quantum mechanics to electron degeneracy, and then to things like neutron degeneracy, even Chandrasekhar himself to these advanced ideas, they've all been connected by black holes. This is the key and the point of the story, that black holes can connect and link these disparate ideas and subjects so well. The next way to see this linkage effect is through 2 smaller stories, the pervasiveness of black holes in popular culture, and one very famous story about Stephen Hawking. Let's start with Hawking and his famous bet with Caltech physicists Kip Thorne and John Preskill. This bet was between Hawking and Thorne on one side, and Preskill, with assists from other scientists such as Leonard Susskind, Gerard 't Hooft, and Juan Maldacena, on the other side. The prize, an encyclopedia chosen by the loser. The subject, the black hole information paradox. This paradox is very interesting and worth diving into, but first we need to clarify some things. First of all, what information means when talking about quantum mechanics. Information refers to the organization and state of the particles that make up something. For instance, if you had a book, the quantum information would be referring to the makeup of the atoms and their arrangement within the book. Second, black holes in general. According to Joe Flasher, a former astrophysicist, there's still some serious misconceptions out there. So black holes are what happens when a sufficiently massive star dies and collapses. All its mass gets crushed down by its own weight to an infinitely tiny point with a staggering gravitational pull. The event horizon, the shell around a black hole, is the distance at which light can no longer escape the gravitational pull, and so that region appears black. Now onto the paradox itself. One key rule of quantum physics is that information cannot be destroyed. To use the earlier book example, if you were to burn the book but keep the smoke, ashes, and gas released in the fire, then interpret the information contained within the book components, you could, in theory, remake the book perfectly. Black holes seemingly break this rule. Since black holes do not live forever and they do emit heat, courtesy of Hawking radiation, they eventually die. But heat can't carry quantum information out of the black hole, and when it eventually dies, nothing is left over. So it would seem that information about anything lost to the black hole in its entire lifetime is irretrievable. It should evaporate along with the black hole itself when it dies. But according to quantum physics, this can't be the case, hence the information paradox. So this is what the three scientists are wagering about. Hawking and Thorne believed that information was truly lost, and quantum mechanics was wrong, and Preskill believed that information had to escape the black hole somewhere. This debate became very well known, and Hawking's concession of it in 2004 made scientific headlines. What caused Hawking to concede was that Preskill's side had come up with the idea of holography, a brutally complex quantum theory that 3D space can be described by its 2D exterior. This idea is far too advanced to try and explain here, but it allowed Preskill's side to prove that somehow the information inside a black hole does eventually find its way back out to the universe. So that's one of the two stories. The next is showing just how far black holes have spread into popular culture. Black holes have made some very obvious appearances in pop culture. Most notable among these is, of course, Interstellar and its black hole Gargantua. As mentioned before, this is one of the best and most accurate imaginings of a black hole. This movie went deep into science, proving black holes to once again be an avenue to these deep scientific mysteries. Wormholes were brought up, explained, and even used by the characters. Time dilation was not only used, it was essentially an antagonist, and when falling into Gargantua, the depiction of what that would look like is as spot on as can be made. This is an extremely well-made black hole and informed a lot of people about very interesting, very complicated scientific subjects. Another example like this is in 2006, just 2 years after Hawking conceded a bet, a Doctor Who episode aired, titled The Impossible Planet. This episode followed the 10th Doctor and his companion Rose as they landed on the titular Impossible Planet. This planet was so impossible because it was in a stable orbit around a black hole. This nameless black hole was more limited than Nolan's Gargantua, both in scientific detail and the quality of the depiction. But it still got explained and was still plot relevant and taught people interesting things about black holes. These are just the big examples, and this is by no means an exhaustive list. What's more interesting is less the big experiences and more so the little ones. For instance, in almost any sci-fi game of any kind, you will find black holes. You can find them in games like Overwatch 2, where this character Sigma, an astrophysicist, fires black holes. Destiny 2, where the Graviton Lance shoots micro black holes. No Man's Sky, where they are a dangerous way to travel. Apex Legends, where a character weaponizes a black hole. The list goes on. Find a game that deals with sci-fi, and you will almost always find a black hole. If you look for it, anything in pop culture that deals with sci-fi practically always has a black hole. They're everywhere, connecting your everyday television watcher, moviegoer, and gamer to a deeper and richer interstellar mystery, whether or not they even know it. So far, we've seen how black holes got their start. From the beginning, they gave scientists a complex link to deeper scientific mysteries. They proved to be an avenue through which many important scientific ideas were discovered, even as people were trying to prove they didn't exist at all. Then we saw how a notable modern example continued this idea, with black holes once again proving to be an invaluable tool for learning more about the universe. Finally, we saw how omnipresent black holes are in pop culture, how they connect scores of people to a deep, complex idea, often without them even knowing. Now, to finish off, I'm going to leave you with a somewhat recent development in our understanding of a black hole singularity, one that, who knows, might even connect you to a whole new field of science. When you fall into a black hole, you obviously can't escape. Most people think this is because the black hole's gravity pulls you in, and its gravity is so immense you can't run away. This is true, but not in the way you think. You can't escape to space or even move away from the singularity once in the black hole, because the singularity isn't in space. Earlier, I said that black holes are what happens when a star's mass condenses down to one infinitely small point. This is true, but I never specified what kind of point. A singularity is not a point in space. It's a point in time. When you fall into a black hole, the singularity becomes your future. You can't escape it, because it plays by different rules. You can't escape a singularity any more than you can escape tomorrow.